Hi, Shalom, and welcome to our virtual event, Minding Human Language, New Bridges Built in the MILA Center between Mind, Brain, and Language. My name is Orly, and I would like to welcome everyone who joined us today to the event of the Cukier-Goldstein-Goren Center for Mind, Cognition and Language, MILA, at the Sagol School of Neuroscience at Tel Aviv University. The MILA Center brings together outstanding young researchers from different faculties and creates a framework for exploring new connections between mind, cognition, and language. Today, we will hear from 8 young researchers about their innovative work in those fields. Due to limited time, it won't be possible to ask questions online, and if anyone is interested in more information, please feel free to contact me and write me afterwards, and I will be happy to connect you with the relevant researchers. First, I'm happy to introduce you to MILA's managing team, Professor Yossi Yovel, head of the Sagol School of Neuroscience, Professor Julia Horvat, steering committee chair, and Professor Naama Friedman, academic director. Please.
So, hi everybody, I'm Yossi Yovel. Thank you, Oli. I'll share my screen. Let's see if this works. Oli, do you see my screen now? And if I do this, do you still see my screen?
Yes, we see it.
Okay.
Now we see all the information. Go back to presentation mode. Okay, great.
You see now presentation mode, right?
Yes.
Okay. So, thank you, Oli, and welcome everybody. I'm very happy to open this first, I think, at least first since I'm head of school, mini symposium of the Cukier-Goldstein-Goren Center for Mind, Cognition and Language, MILA. We've decided to dedicate this event to honor the memory of Alex Goren, who passed away exactly 1 year ago. And in preparation for the event, I read about Alex. It's always, you hear all of these names of centers, but you never really know the people until you read a little bit about them. So I'm glad I had this opportunity, and I've discovered that Alex was really, really great. I can't say anything more than just a great human being. He was a real philanthropist with a true passion for science and education in Israel. He contributed to many universities, of course, Tel Aviv University, but maybe foremost Ben-Gurion University, where he was the chairman of the board of governors for many years. And although I never met him, and Selina, you can tell me if I'm right later on, but I'm sure that the decision to invest in Ben-Gurion specifically, it was part of his vision of investing in the Negev. Investing his time and energy in the Negev. And on a personal note, I can say that I was born and raised in the Negev, and I've always seen it as my home. So I apologize in front of Tel Aviv, the city, and Tel Aviv, the university, but I've always had my own warm corner for the Negev. Alex was also, of course, a great supporter of Tel Aviv University and specifically contributed to the establishment of the MILA Center for Cognition, Mind and Language that was established by the Cukier-Goldstein-Goren Foundation. And I've never personally met Alex, unfortunately, but I can see his impact every day. I can see it through the work of students and researchers who are members of the MILA Center. And I think that it's important to emphasize what a huge contribution such centers can have on basic sciences. So it's not always easy to raise funding for such basic science. Some fields are very easy to raise funding for, like cancer or whatever, corona these days. And it is these basic sciences that form the foundation of other sciences. And therefore, I think the contribution of a center like the MILA Center is huge, much greater. The impact it can make is much greater than many other centers that I can think of. And I'm also happy to see that that many of the family members have joined us, some of which I've met already, like Selina, some of which I've read interviews with like Martin, and others that I've only heard about. And I'll be happy to to meet in the future. So we really have a packed and fascinating, I think, schedule. I'm really looking forward to hearing some of the talks, all of the talks, actually, I should say. I'm therefore going to be short, and I'll let Julia and Naamat speak. I just want to say again, thank you to Orly Segev, who's joined us recently and really brought a lot of new energies to the MILA Center and to other initiatives that she is involved with, and she's also going to moderate and lead us tonight. So thank you very much, and Julia, the floor is yours.
Unmuted. Thank you very much. It's really a great pleasure for me to welcome you all at this year's meeting of the Cukier-Goldstein-Goren MILA Center for the Research of Mind, Cognition and Language. And a special welcome and thank you to members of the family, to Selina Goren-Komeran, that I met in person, and all other members of the Cukier and Goldstein-Goren families, the donors of our center, who we have the pleasure to have here with us today, although unfortunately not in person. I'm Julia Horvath, as you heard, professor of linguistics and the new chair of the MILA Center's steering committee. The research presentations to follow are a representative sample, giving just a taste of the ongoing, very diverse and productive interdisciplinary collaborative investigations that the MILA Center has made possible and stimulated ever since its foundation. As today's program will show, the research projects undertaken cut across disciplines, cut preset and cross preset departmental and faculty units, and cover a very broad range, but eminently coherent range of research goals and topics. These research projects derive from the collaborators' creative integration of ideas from their particular disciplines and are pursued using correspondingly diverse research methodologies. The subject matter the MILA Center focuses on is the nature, mental representations and mechanisms of humans' language capacity and its relation to other aspects of cognition. To acquire and use natural languages is a fascinating, universal, and uniquely human ability. This ability, investigated from multiple perspectives, can provide an intriguing window into the human mind, cognition, and ultimately into the representations and neural mechanisms that implement this complex, abstract, unconscious knowledge in the human brain. So no wonder that the relevant lines of investigation cut across and connect different domains of inquiry as diverse as neuroscience, modern theoretical linguistics, investigating the human linguistic competence, its fundamental properties and modular architecture, cognitive psychology, investigating aspects of the language capacity in relation to other aspects of cognition, or the domain of psycholinguistics, exploring language processing, production, and the acquisition of language by children, as well as the domain of neuropsychology and education, investigating the diagnosis and treatment of the various types of language impairments and deficits. Accordingly, the research methodologies employed in these collaborative interdisciplinary investigations also vary, ranging from neuroimaging methods such as fMRI and testing during brain surgery to quantitative surveys of phenomena in linguistic corpora, and from behavioral experiments involving various subtypes of typical and language impaired populations to computational models for testing theoretical linguistic hypotheses about natural language grammars and their learning. It is this rich diversity of perspectives in conjunction with the coherence of its broad research program that makes the MILA Center's mission so important, so timely, and also so intriguing. And I hope the following presentations will be seen by all of you as validating this claim. Nama.
Hi, everyone. Happy 22222. It's not a coincidence that we selected this lovely date for our MILA Day. It matches the vision of the center perfectly. MILA is all about building bridges between at least two disciplines, mind and language, fostering collaborations between at least two collaborators, researchers, and giving a second thought to connections that seem, on first thought, improbable and new. The vision of the MILA Center is that of creating new interdisciplinary collaborations between researchers in Tel Aviv University to start thinking together on language and mind from multiple directions. And this is exactly what we do with the MILA projects. So the idea was that researchers who have never collaborated before submit a proposal together for a new research that connects language and mind. And today you will see that through these 2 points, language and mind, very, very many lines can be drawn. MILA allowed us to discover how many researchers in Tel Aviv University are interested in language and in mind, and what beautiful and insightful research is done here, and how people are open to a bridging between language and brain and mind. The vision of MILA also includes the support of collaboration of researchers from MILA with researchers of language and mind abroad. And this is what we do through inviting guest lectures and courses that MILA supports in all domains of language, cognition, and mind. In the past years, leading researchers in the field have already visited MILA, and we have a very distinguished line of researchers who will be talking to us in the coming year. MILA is also about supporting the academic development of bright young researchers, MA, PhD, and postdoc students, creating research opportunities for them. And the tools that we selected to do so are the MILA projects. So the interdisciplinary projects that encourage new collaborations that I told you about between researchers from different fields are actually supporting, the funding is supporting young researchers. The graduate student who works on this project. And working on all aspects of a research project early in the academic path of a student helps in their development as researchers and prepare them to build their own lab later. And this is also the rationale behind our MILA Day today. The speakers are the students, the young researchers in charge of the MILA projects. As Yossi told you before, our meeting today is dedicated to the memory of Alexander Goren. Alex was very supportive of MILA. I was fortunate enough to meet him and talk to him. And in the meetings that we had, he was very active and interested and excited about language and about brain and about research. And he was listening very carefully and asking many great questions, always to the point. And he will be missed, but we are very, very happy to have other members of the family here with us, Selina and Martin. So let us now turn to hearing how many creative and groundbreaking lines our researchers can draw between 2 points, mind and language.
Thank you very much, Yossi, Julia, and Naama. And now let's move on to the wonders of science. We're going to start with Neta Chalutz. Please unmute yourself and the stage is yours.
Thank you, Orly. Let me just share my screen. Okay, can you see the presentation mode?
Yes.
Yeah, good. Okay, so first of all, I'm very happy to open this event with telling you about our research. In our research, we test how language is processed in the brain by identifying the brain mechanisms that are damaged in individuals who have reading impairments or syntactic impairments. So our brain is made of special cells called neurons, which pass electric signals through long fibers called axons. Axons are surrounded by myelin, which insulates them and increases the rate of their electric signals. And brain areas communicate with each other through pathways of many axons. And because of the white color of the myelin surrounding the axon, these pathways seem seem brighter than the areas including the cell bodies and are called the white matter. The white matter pathways or tracts connect different regions within the same hemisphere. They can connect similar regions between the hemispheres, and they can connect the cortex of the brain with lower parts of it, such as the brainstem or the spinal cord. In order to quantify and analyze the properties of white matter structures in the brain, a method called diffusion tensor imaging, or DTI, is used. The anisotropic nature of the diffusion of water molecules in the brain, which means that they can travel a longer distance along the axon than perpendicular to it. This allows for the mapping and visualization of white matter structures in living people. DTI studies in the last decades has revealed that not only gray matter or cell body structures, but also white matter properties are related to cognitive abilities, and specifically to language abilities and to language impairments. So next, I will tell you a bit about what we already know of specific types of dyslexia and syntactic impairments from neuropsychological research. Analyzing the error patterns of individuals with different language impairments allows for construction and updating of cognitive models representing the different stages involved in language processes. In the reading domain, more than 20 different types of dyslexia have already been identified. And each type of dyslexia can be associated with an impairment to a specific component of the dual root model for single word reading that you can see here. So for example, if someone has an impairment in the early stages of the visual analysis of the word, in a stage of letter position encoding, this can result in letter position dyslexia, or LPD. And this impairment causes transpositions of letters within the word, especially when this results in another existing word. So for example, an individual with LPD can read the word files as flies or slime as smile. In another type of dyslexia, surface dyslexia, the impairment is in another location, in the long-term store for the written form of the word, for its phonological form, or in the connections connecting them. This leads to reading words through grapheme to phoneme or letter to sound conversion, and causes difficulty in reading words with irregular spelling or words that may sound as other words when read through grapheme to phoneme conversion. So for example, now can be read as no, and face as face, and the irregular word stomach as stomach. Because dyslexia is not a single impairment, as we saw, and may result from deficits in many different components in the reading process, it is very likely that the brain regions related to the impairment will vary depending on the specific type of dyslexia the individual has. Since previous studies usually related to reading impairments very generally and group together individuals with different types of reading impairments, the underlying brain regions have not been detected yet. Considering syntax or a sentence structure, studies characterizing the error pattern of individuals with syntactic impairments showed that different aspects of syntax can be impaired as well. For example, while some patients have difficulties in structures involving higher nodes of the syntactic tree, which includes WH questions, but also embedded clauses, other patients have deficits only in sentences in which the canonical order of the sentence is changed. So for example, when the object appears prior to the subject in the sentence. In this sentence, for example, the canonical order is subject, verb, object. The grandma kissed the girl. However, in order to ask a question about the girl, the object moves to the beginning of the sentence and appears before the subject. Which girl did the grandma kiss? This is called syntactic movement. So some patients have difficulty only in structures involving this type of structure. In addition, research about connectivity and syntactic impairments has focused so far mainly on aphasic patients who had acquired impairments, but the involvement of white matter tracts in people with developmental syntactic difficulties has not been explored yet. In our study, we use what is known from neuropsychological research about the specific types of dyslexia and of syntactic impairment that I just told you about, and we associate specific types of deficits with white matter tracts in the brain. We test individuals with and without dyslexia and with and without syntactic impairment in a very broad battery of 13 tests, including tests for reading aloud and silent reading of words sensitive to different types of dyslexia, and tests for production, comprehension, and repetition of sentences with structure sensitive to syntactic impairments. This will enable to identify individuals with specific syntactic impairments. Additional tests are administered to participants that we suspect to have a specific impairment to better characterize their pattern of errors. The participants also undergo DTI scans, which allow us to analyze the properties of their white matter pathways. We plan to analyze the results in two main ways. The first one is at the group level. We want to compare individuals or groups with the same types of dyslexia or syntactic impairments to the control group and test which white matter tracts are associated with each impairment. The other way is to test for correlations between specific reading and syntactic abilities and properties of white matter tracts in all of the participants, with and without impairments. This will allow us to reveal which white matter tracts are correlated with reading and syntactic abilities. So far, we have already tested 32 participants, 30 of which already underwent the DTI scan, and we already identified some participants with dyslexia and syntactic impairments. So I'll give you some examples. This is one participant who had a syntactic impairment. When we asked him to explain the sentence, "I saw the teacher that the girl liked," which has a syntactic movement in it, his response was, "The teacher liked the girl," which is the opposite from the roles in the sentence. When we asked him to repeat the sentence, "Which woman did the girl draw?" his response was, "Which girl, which what?" He was very confused. We repeated the sentence again, and he again started with "which girl," and only then could repeat the sentence correctly. Another participant with surface dyslexia, when reading aloud words, she read through grapheme to phoneme conversion. So she read the words as other existing words in Hebrew that maybe read the same. So she read sha'ar as sha'ar, ma'acha as ma'akeh, which is similar to reading the word face as face. We are now working on analyzing the DTI results and test how the white matter properties of different tracts are associated with specific reading and syntactic abilities and impairments. And we expect that very soon we will be able to reveal the white matter tracts, which are crucial for specific reading and language processes, which will of course broaden what we know about how reading and language processes are organized in the brain. So many thanks to MILA Center for funding this project, and thank you for listening.
Thank you very much, Neta. And we're going to move on to Einav Flick, please. Einav, please unmute yourself.
Okay.
Yeah, okay.
Can you see the presentation?
Yes.
Thank you very much, Orly. And thank you to the MILA Center. And, much research in sentence processing has focused on the processing of local ambiguities as in one. Here, when we reach the ambiguous phrase "the vet" during reading, we can in principle attach it either as the object of scratch or as the subject of an upcoming verb. The second attachment would be the correct one if the sentence continued as in to. Many studies show that in such sentences, readers slow down at the second verb, took off in this example, indicating that they initially read here after the dog scratched the vet. In other words, readers usually attach the vet as the object of scratched, rather than as the subject of took off. These findings, among others, led to the formulation of late closure, a processing principle dictating that incoming items are attached to the phrase currently being processed, instead of opening a new phrase. Ambiguities where a phrase can be analyzed as either part of the preceding or following phrase appear in additional structures, which were not studied as extensively. For example, in the ambiguous sentence 3, where the adverb yesterday is preferably attached to the preceding clause. Or in this title. At least 3,000 people experienced reading difficulty here. Processing strategies are deduced from reading time and interpretation patterns. Here we'll argue that they can also be deduced from the addition of a conjunction during copying, and that the late closure strategy was operative 2,000 years ago. Our corpus is the Great Isaiah Scroll that was found in the Qumran site. The scroll is written in Hebrew, and it is dated to the 2nd century BCE. It is a version of the canonical biblical book of Isaiah that we know today. It is thought that the scroll was copied from an early version of Isaiah. The scroll exhibits over 2,000 differences from the biblical version, including omissions, additions, and substitutions of letters and words. Here we focus on one type of difference, namely additions of the conjunction ve, meaning and. We found 241 additions of the conjunction in the scroll. Interestingly, almost a third of these additions appear in ambiguous verses, where a phrase can attach either to the preceding or the following clause, as in the sentences we saw earlier. Ambiguity was extremely prevalent in the source text for two reasons. First, the text lacked punctuation, which only evolved several hundred years later. Second, Biblical Hebrew presented extremely flexible word order, with phrases moving around freely in the sentence. Let's see some examples of ambiguous verses and how they were copied. This verse has two possible readings, because the adverb together can attach either to the preceding or following sentence. Either the cow and the bear feed together, or the children lie down together. Here, the noun wine can either be the object of drink, that is, they shall not drink wine, or the subject of bitter, that is, wine shall be bitter. The biblical text used today has been furnished with punctuation marks that indicate what the accepted reading is. If we look at the scroll, we see that ve and was added in both verses. As I said, there were 77 cases like these where the conjunction was added in ambiguous verses. For each of these, we coded two factors. First, whether the addition complied with late closure, namely whether the conjunction was added after the ambiguous phrase. In the two examples we just saw, this was the case and was added after the ambiguous phrase in line with late closure. We found that 63 out of 77 additions of and complied with late closure. But remember, we said that the source text has commonly accepted reading tradition. Perhaps the additions are not due to a processing strategy, but simply reflect this reading tradition. So for each addition, we also coded whether it accords with the reading tradition. How can we know what the reading tradition is? It can be gleaned from the canonical biblical text, which has what we call cantillation marks, te'amin. The cantillation system, which contains punctuation instructions, was superimposed upon the biblical text around the 8th century CE, but it reflects a much earlier tradition. In our verse, there is a cantillation mark on the ambiguous word, which is equal to a comma. It tells us that in the reading tradition, there was a pause after wine, namely wine was attached to the previous verb. So when we look at the addition of and in the scroll, we see that in this case, it is in line with the reading tradition. In contrast, in this case, where the addition of and also complied with late closure, if we look at the cantillation marks, there is a comma equivalent on the word before the ambiguous adverb. So in the reading tradition, the adverb was part of the following sentence. The scroll is at odds with the biblical text. Late closure was strong enough to generate a textual difference in this verse. So as I said, for each addition, we coded whether it complies with late closure and whether it accords with the reading tradition. And here are the results. Out of the 63 additions that comply with late closure, in 30 cases, the addition was in line with the reading tradition. Significantly, in the other 33 examples, late closure overrides the reading tradition. Only 4 additions were not consistent with both late closure and the reading tradition. So to summarize, we have shown that the late closure strategy is a powerful factor in the copying process of an unpunctuated text. And these data provide the earliest evidence, as far as we know, for the operation of the sentence processing strategy. Thank you.
Thank you very much, Einav. And we're moving on to Yarden Ashkenazi. Please.
Okay. Okay, so hi everyone. My name is Yarden and I'm a speech therapist and a graduate student at the Department of Communication Disorder of Tel Aviv University. I'm pleased to present to you the research I'm part of, along with several other students, under the supervision of Dr. Katie Bradkin, who is together with Debbie Rand, is the principal investigator. So this research is about rehabilitation of stroke-related language and cognition disorders using non-invasive brain stimulation. So when a stroke affects language area in the brain, a disorder that we call aphasia cause, which may be evident in speaking, comprehension of spoken language, reading and writing. The inability to express and understand a message significantly impairs patients' quality of life and lead to social loneliness and less participation in society. One of the main difficulties for people with aphasia is naming, which means giving a name to an object or an action. Try to think about the last time that you had a word on the tip of your tongue and how much frustration it caused you. For a person with aphasia, this can happen again and again, several times in one sentence. In our study, we focused on the interplay of aphasia with bilingualism. So the effectiveness of behavioral therapy available today is partial. So researchers have begun to look for alternatives by integrating advanced technologies along with therapy to increase its effectiveness. The tool we use in this study is transcranial direct current stimulation, or TDCS. It's a device that transmits low current to the brain through electrodes placed on the scalp. In our study, we chose to stimulate an area in the frontal lobe called dorsolateral prefrontal cortex, or DLPFC. It supports both language processing and executive functions that are high-level cognitive abilities. In the present study, we examined a combination of language therapy in Hebrew, along with the anodal stimulation of TDCS over the left DLPFC area for Russian Hebrew speakers with aphasia. The improvement is assessed in trained and untrained words in Hebrew and Russian and in executive functions. Each of our participants received 24 sessions, where the first sessions focused on assessing language abilities and on constructions of the set of words for treatment. Next, we perform 2 sets of treatments with speech therapists, each of 5 sessions in 2 weeks. In one set, the electrical stimulation is active, and in the other set, it is a sham stimulation, which means a control condition, where the electrodes are attached, but no current is delivered. Before and after each set of treatment, naming and executive functions are assessed. Finally, we return to the participants 2 months later and check their achievement in maintenance. So I will now present to you very short videos of one of our participants before and after the treatment. I think they illustrate well the naming difficulties that the person with aphasia experiences, and they show the person himself. For a person with aphasia, every word counts. We of course obtained permission to show these videos. So you can see at the left, the patient tried to retrieve the word spider, which is a akavish, before the treatment, and in the right, after the treatment. And after the therapy.
Abakish, akavish. Abakish.
So now he's looking for the word turtle, which is a tzav.
Brilliant.
And after the therapy?
So,
And here's a third example when he's looking for the word sculpture. In Hebrew, it means pasal.
sculptor.
And after therapy?
פסל.
I want to present now the change in all the patients we have examined so far. At the moment, it is not possible to perform analysis at the group level. So we have performed a calculation as shown here at the individual level. The formula we use is presented here, and we define the change as being meaningful when it was above 30%. You can see in this table the meaningful changes marked in dark in our participants when naming in Hebrew. You can see that all the participants improved after they received real stimulation in the set of words they were trained on. Some of them also improved during the Shams condition, but not as much. There was also evidence of greater improvement in untreated words in Hebrew and in maintenance of the performance after 2 months. Here you can see the change in Russian language. As you can see, there is not much improvement in the untreated language. Currently, at the individual patient level, we didn't see changes in executive functions assessments. So to summarize, until now, we found greater improvement in naming in words they were trained on in Hebrew in all participants, and greater maintenance and transfer to untrained words in Hebrew for most participants, all following active stimulation compared to sham stimulation. We also found no improvement in executive functions and no transfer of treatment effects to the Russian language in most participants. So to conclude, brain stimulation with TDCS seemed to enhance the benefits of traditional language therapy in bilingual speakers with aphasia. The next steps will be recruiting additional participants and conducting group statistics. I would like to thank you all for listening and thank the MILA Center for funding this research.
Thank you very much, Yerden. We're moving on to Dr. Moshe Bar-Lev, please.
Thanks, Oli. Hi, everyone. What I want to begin with in this talk is asking you to imagine a language that that you don't know and that, in fact, no one knows because it doesn't exist. So to know what you need to imagine, first, look at this sentence in English. Miriam did not read both Anna Karenina and the brothers Karamazov. It's a slightly complex sentence, and we can characterize what it means by looking at all the situations in which we would say the sentence is true. So in a situation where Miriam read Anna Karenina but not the brothers Karamazov, and in a situation where she read the brothers Karamazov but not Anna Karenina, as well as in a situation where she didn't read any of these books, we would say the sentence looks like it's true. That's a way to describe what it means. And now let's think of this other language, which is a made-up language, and we call that language Glinglish. And imagine that in this language, instead of saying this complex sentence in English, you can say the same thing with a more simple sentence, which goes like this: Miriam read Anna Karenina, and the brothers Karamazov. So in this language, you have a word, this NAND word, which allows you to express this meaning, which in English you would have to use a complex sentence for, in a simpler way. So this looks like a fine language and perhaps a language that we would like to have because it looks like a bit more efficient than English. Now here's the striking thing about Glinglish. It doesn't exist. If you look at all the languages of the world, you are not going to find any language, at least no language that we know of, where you have a word like NAND in Glinglish. This kind of generalization is a semantic universal. It's a generalization that's true of all languages and tells us something about what meanings can be expressed in natural language and in what ways. and studying semantic universals is something that has been central to the study of language for the last 50 years or so, because they open us a window into understanding what language is, what its nature is. Because if we see something that's true of all languages, no matter how unrelated they are to each other, how far away from each other they are, this looks like something that can teach us something deep about how language works. Of course, the question is, what does it teach us? Does it teach us something about language? Does it teach us something about the mind? So there are several possible options here. So perhaps the reason why we don't have a language like English is that there are cognitive limitations. So perhaps there is, it's impossible to store in our mental lexicons a word whose meaning is NAND. That would be one possibility. Another option is that we can store a word with this kind of meaning, but it's a more complex word. It's a more complex meaning than, for example, a word like and. So we would, in some way, prefer not to do that in some sense. Another option is that there is no actual problem with our mental abilities if we want to have a language like NAND, because we can understand what it means. But for some reason or other, it's not going to be very useful in conversation. So that's why we don't see it in any language. Yet another option is that it's going to be very difficult for language learners to learn a language where you have a word like NAND. So these are several options for why you would have this fact, this semantic universal, that you don't have any language with a word whose meaning is NAND. These are all possibilities that people have suggested might be the reason why we don't have that. But of course, there could be other reasons. Now, what we did in my work with Ronnie Katzir is finding a new source for semantic universals, one that hasn't been considered before, and one that we argue gives a better explanation for why we don't have, for example, a language like English, why we don't have a language with a word whose meaning is NAND, and also why we don't have some other languages that you could imagine. And this, the idea that we have is what we call communicative stability. But before I can tell you what this means, I have to tell you something about how can we even think about communication in languages that do not exist, because obviously we cannot go to speakers of English and look at how they communicate with each other, because there are no speakers of English or any language with a word like NAND. So what we did instead was use a computational model of how communication works. It's called the Rational Speech Act model. It's been used quite extensively in recent years to simulate how communication works. And using this model, we can simulate how communication would look like in imaginable languages, for example, in English. Now, what we found was that that there is a line separating between actual languages like English and non-existent languages like English, which is that communication in actual languages does not depend on something that communication in non-existent languages does depend on. And this thing that communication in non-existent languages like English depends on is what the speakers and hearers think are more likely situations. So in English, the choices that speakers and hearers are going to make in conversation are going to be dependent on what situations they think are more likely and what situations they think are less likely. And the idea is this is, as a result of that, these languages are going to become unstable, and they're going to give rise to miscommunication. I know this is a kind of abstract. I hope I'm going to be able to illustrate this idea in a way that's more understandable, even though, of course, I'm not going to be able to give you all the details of how the model works and all the assumptions that go into this. But the way you can think about the idea is that what we observe with this model is that if you were a speaker of English, you would be in a situation that's like the situation in the Tower of Babel, where people cannot understand each other. But this time, not because they speak different languages, but because even though they do speak the same language, they can miscommunicate because they do not know each other's assumptions about what's more likely and what's less likely. So let's see an illustration of how why it's a bad idea to have choices of speakers and hearers in a language be dependent on what they think is more likely and what they think is less likely. So suppose we are speakers of English, so we have this kind of sentence available to us. Miriam read Anna Karenina and the brothers Karamazov. And this sentence, we said, is true in 3 situations. These 3 situations where Miriam read Anna Karenina but not the brothers Karamazov, one where she only read the brothers Karamazov, and one where she read neither of these 2 books. And now suppose we have a speaker who thinks that Miriam read the brothers Karamazov but not Anna Karenina. So the piece of information that the speaker wants to get through to the hearer is that this is the actual situation. This is what actually happened, that Miriam read the brothers Karamazov but not Anna Karenina. What we see with the model that we used is that here is something that's going to be possible in this language, is the following. So here's our speaker, and the speaker is a rational speaker. She wants to decide what message she wants to use to convey this piece of information, which is that Miriam read the brothers Karamazov but not Anna Karenina. What would be the best choice? Now she imagines what a hearer, which is this guy here, would think if she makes different choices. Now, one thing that she thinks is that it's more likely that Miriam read the brothers Karamazov and not Anna Karenina than the other way around. So she also thinks that the hearer is going to think the same thing. Now, based on that assumption, she is going to choose using the sentence with NAND that we've seen, because based on that, she can, if that's the assumption about likelihood, she can be sure that the hearer would understand what she's saying if she's using the sentence with NAND as conveying the piece of information that she wants to convey, namely that Miriam read the brothers Karamazov but not Anna Karenina. But this is actually really dependent on her assuming that we are in this situation where reading the brothers Karamazov but not Anna Karenina is the more likely situation. Now, suppose this speaker goes on and says this sentence with NAND, but what she doesn't know is that the hearer has a different assumption about what's more likely and what's less likely than what she does. So instead of thinking that reading the brothers Karamazov but not Anna Karenina is the more likely situation, the hearer thinks the opposite, that reading Anna Karenina but not the brothers Karamazov is the more likely situation. And as a result of that, the way he would understand what the speaker said would be as saying that Miriam read Anna Karenina and not the brothers Karamazov, which is exactly the opposite of what the speaker wanted to convey. So here's why it's a bad idea to have a language where the choices of speakers and hearers depend on what they think is more likely and what they think is less likely. In this kind of language, you can have a speaker who uses a sentence like NAND because she wants to convey a specific information, namely that Miriam read the brothers Karamazov but not Anna Karenina. But because the hearer has different assumptions from hers about what's more likely and what's less likely, he's going to understand exactly the opposite thing than what she wanted to say, which is that Miriam read Anna Karenina but not the brothers Karamazov. So that illustrates why we do not want a language where speakers and hearers' choices depend on what they think is more likely and what they think is less likely. So here's what we found, our discovery in a nutshell. What we found was the following. If you look at communication in non-existent languages with this model, what you see that it depends on the speakers and hearers' assumptions about what's more likely and what's less likely. And as a result, communication is going to be unstable and inefficient in these languages. Now, on the other hand, if you look at actual languages like English, you see both in the model and in real life, when you look at speakers of English, for example, and also speakers of Hebrew and other languages, that the choices that speakers and hearers make are for the most part independent of what they think is more likely and what they think is less likely when they want to convey a specific piece of information. And as a result of that, these languages are stable and they are efficient. There is much less room for miscommunication. Situations like the one we've seen with that might happen in English are not going to happen in English. And that's why it's a much better language. So what we propose then is that you can explain why you don't find languages like English by only thinking about what communication would look like if you had a language like English. The idea is it's not going to be a very effective tool for communication, a language like English, and that's why it's not going to survive when languages evolve. Okay, so to just to give you a bigger picture of what we do in this project, what we try to do is explore semantic universals in a way that would help us understand language, but both as a cognitive system and as a tool for communication. So what I told you about today was how we can use the facts about how communication works to explain some semantic universals. Specifically, the semantic universal is responsible for the fact that we do not have a language like English, a language with a word like NAND. But the other part of the work is trying to see how far we can get with explaining semantic universals by considerations of communicative efficiency, and what semantic universals we cannot explain by this. Semantic universals that we cannot explain by looking at how communication works are semantic universals that tell us something very deep about how the mind works. So, and we have some preliminary results about what we cannot yet explain with communicative efficiency considerations. And these are things that tell us something about how the mind works, but this is going to be for another time. Thank you.
Thank you very much, Moshe, Mila's postdoc, I have to say. And for now, we will take a short break of 10 minutes. You are welcome to stretch a bit, and we'll meet here again at 12 minutes past 6. And then we will hear about consciousness, teaching with interactive videos, face recognition, and awake brain surgery. So see you in 10 minutes. Okay, we're gonna start. Thank you all for joining us again. And now we will hear from Dana Harel. Please.
Hi, everyone. 1 second. Can you see my presentation?
It's not in presentation mode.
Yeah, okay, now it is. So perfect. Yeah, okay. So I'm Dana Harel, and I will present my research on the role of consciousness in sentence processing. I would like to thank Professor Liad Mudirk and Professor Orna Peleg. My work has been done under their supervision. So understanding written words during sentence comprehension requires readers to rapidly access and integrate different sources of information, including lexical knowledge related to the word itself and contextual knowledge related to the context in which the word is embedded. The present study investigated the role of consciousness in this complex process. A growing body of evidence indicates that single words can be processed even in the absence of awareness. However, it remains debated whether higher level processes, such as integrating a word with its preceding context, can also be performed unconsciously. To tackle this issue, the present study used ambiguous words whose meanings depends on the context in which they appear. For example, the word bank which is associated with two different meanings, a financial institution and a riverside. Thus, when its processing entails a selection of the contextually appropriate meaning. For example, when we read the sentence "Bill stole from the bank," we think about a financial institution. And when we read the sentence "Bill fished from the bank," we think about a riverside. Now, to investigate genuine integrative processes, the present study used ambiguous words with meaning belonging to two different syntactic classes, a noun and a verb. For example, the Hebrew homograph ambiguous word etzem or atzam has two different readings. Etzem, which is a bone, a noun, and atzam, which is closed his eyes, a verb. Thus, the ambiguous word was embedded not only in semantically biasing context, but also in syntactically biasing context. And this allowed us to create a strongly biasing context without using lexical associates. So the study included 3 experiments. In all experiments, 3-word sentences were presented 1 word at a time, context, ambiguous word, and a target. And participants were asked to make a word, no word decision on the target. They were asked to judge as quickly as they could whether the target is a Hebrew word or not. In the critical trials, the second word was a noun-verb homograph, etzem, atzam, and the first word served as a context word, creating an expectation for either a noun or a verb. For example, when we read the word shavarti, I broke, we expect a noun, I broke a bone. And when we read the word the baby, we expect a verb, the baby closed, for example. So now we compare 2 conditions, a match condition and a mismatch condition. In the match condition, the target, the third word, was related to the contextually appropriate meaning of the homograph. It means that the target was congruent with the preceding sentence. For example, I broke a bone in the body, or the baby closed his eyes. In the mismatch condition, the target was related to the contextually inappropriate meaning of the homograph. For example, I broke a bone, his eyes, or the baby closed in the body. Means that the target was incongruent with the preceding context. Faster and more accurate responses in the match than in the mismatch condition indicates semantic integration processes. In other words, it indicates that the third word was processed in accordance with the preceding context, and when it was consistent with it, the identification was faster, easier and faster. Importantly, to test the role of consciousness in these sentence level integration processes, the first 2 words were either masked or unmasked. In experiment 1, all 3 words were displayed without masking, the context, the ambiguous, and the target. In experiment 2, the first 2 words were masked, the context and the ambiguous word. And in experiment 3, only the first word, the context word, was masked. A match effect, faster response in the match than in the mismatch condition, was obtained only in the first experiment, only in the unmasked experiment, as you can see. When the first 2 words, in experiment 2, when the first 2 words were masked, there was no difference between the contextually appropriate meaning and the inappropriate. Means that there was no effect, no congruency effect. In other words, there was no difference between the match and the mismatch condition. And interestingly, even when only 1 word was masked in experiment 3, the context word, there was no evidence of a sentence level integration. Means that there was no difference between the match and the mismatch condition. The results provide support for the view that consciousness might be needed for a sentence level semantic integration. Thank you all. I want to thank the MILA Center for funding the research, and hope you enjoyed.
Thank you very much, Dana. Moving on to Nofar Rimon. Please, stage is yours.
Can you see the presentation? Yeah, okay. Okay, so hello everybody. My name is Nofar. I'm a linguistics MA student, and I participate in a research group with Iris Melamed-Gorodisky from the Department of Hebrew Language, Goren Gordon, the head of the Curiosity Lab from the Department of Industrial Engineering, and Einat Gonen, the head of the Department of Hebrew Language. Together, we research ways to promote the morphological awareness of young children through robots and avatars. Today, we'll be presenting our research, Root for Change, in which we taught young children to extract Hebrew roots using interactive videos. The previous research included social robots, which due to COVID-19 were converted to cartoon avatars. Whether you study Hebrew here in Israel or abroad, you probably remember the word sholish, root, from Hebrew lessons, even if you weren't very fond of them. Those three, sometimes four consonants that every word in Hebrew is composed of. So the root of the word, of the verb, rakadti, which is Hebrew for I dance, is rekeded, or rakad. And the root of the noun shemenet, which is Hebrew for cream, is shemenet, or shaman. You'll probably also remember yourselves trying to memorize all the different root classes before exams. Difficult, boring? Well, it doesn't have to. What if I told you that 5-year-olds did it better than you after only 40 minutes of oral instruction and without any theoretical explanations? Our program teaches children as young as 5 years old to extract the root of regular Hebrew words in only 5 short video lessons. The duration of each video was between 6 to 10 minutes, and the overall duration of all lessons was approximately 40 minutes. The teaching method was developed by Dr. Einat Goren, along with Dr. Goren Gordon, who was responsible for the technological parts. Goren and Gordon found an innovative approach made possible only by the combination of two seemingly completely different disciplines. In the videos, the children were introduced with two avatars, Fuzzy the dog and Tutti the cat. Let's watch a few seconds of one of the videos. As you can see, the avatar poses the question, what is the root of the word X? And after giving the children a few seconds to answer, the avatar provides the correct answer along with the complements. The questions and answers are given in a rhythm that resembles recitation, and the avatars encourage the children to actively participate as they decipher the roots alongside the avatars. So basically, the whole program is based on oral instruction only, without any complex theoretical explanations, and it does not require any literacy skills. So it is suitable even for preschoolers. In order to examine the efficiency of our program, we conducted an experiment. The experiment was conducted online from beginning to end, and this enabled us to reach many children of varied backgrounds from all over the country. We ended up with 64 participants that completed all lessons, the pretest and the post-test. In the pretest, we assessed the children's prior knowledge, and since the oldest participants were second graders who had already been formally introduced to roots in school, they were significantly better than preschoolers at extracting them. After completing all 5 lessons, the children took the post-test. So these are the results by class. The left bar of each group indicates its achievements in the pretest, and the right bar relates to the post-test. As you can see, the preschoolers completely closed the gap, and all children significantly improved their root extraction skills. Here you can see the average score of all participants, which increased drastically between the pretest and the post-test from 0.1 to 0.73. This difference was also statistically significant, of course, And it is worth pointing out that not only did children succeed in extracting roots of common verbs, but they also successfully dealt with complex verbal forms, as well as nouns and pseudo-words. Pseudo-words are made-up words that have no meaning, but obey the rules of Hebrew. For example, the pseudo-word yetzrilu, whose root is tzaral. Children managed to extract the root of the word yetzrilu, even without ever hearing this word before, nor understanding its meaning. And now you can say, okay, cool, but what is it good for? So first of all, root extraction skills are essential for high school matriculation exams, but that's only the tip of the iceberg. Research found that explicit morphological instruction, and particularly root-based instruction, improves children's morphological awareness as well as their literacy skills. Moreover, children rely on roots when they interpret unfamiliar words or coin new words. The next steps that we are currently working on are providing a linguistic analysis of the children's answers in order to learn about how roots are represented in our minds, and conducting the same experiment in Arabic. Roots characterize all Semitic languages, and we are curious to examine our method on Arabic-speaking children as well. Although our program is currently extracurricular, due to its ease of implementation and speed of completion, it can be easily integrated in schools in Israel, and with some modifications abroad, serving for instruction of Hebrew as a foreign language. Thank you for listening. I would like to thank Einat Gonen for her guidance and for believing in me, and of course, MILA Center for their generous support, without which all this could not happen. So thank you again.
Thank you very much, Nufar. We couldn't hear your short video if was a volume there.
Yeah.
But it was very interesting. So we're gonna continue now. We're gonna move on to Ninoy Schwartz, please.
Thank you. Do you see the presentation and hear me?
Yes, please put
okay.
In mode. Okay.
Great. Okay, so I'd like to present to you our work on the roles of conceptual information in face recognition done in a collaboration with Dr. Einat Goren under the supervision of Professor Galit Yovel. So I'd like to start at the very beginning. Let's say that you just met this person here at the conference and you want to try to remember him or recognize him for a later encounter. If I'll ask you, how would you try to remember or to encode this face? I think that most of you will say things like, well, I'll look at the color of his hair, the color of his eyes, the shape of the face, maybe if his jaw is square, maybe I'll look at his nose and so on. So most of you will very naturally rely on the physical appearance of the face, meaning rely on perceptual features. However, we know that faces could also be encoded socially, meaning by what we think of them. For example, if this person looks intelligent, trustworthy, dominant. Now, social evaluations aren't arbitrary. They're actually highly correlated among participants. They're done automatically and subconsciously by all of us. And the most interesting part is that they are actually derived from the exact same physical features as perceptual evaluations. For example, trustworthiness is highly correlated with the size of the eyes, with bigger eyes making the face look more baby-like and more trustworthy. Now, most of us tend to rely on perceptual evaluations, but are they really more useful? To examine exactly that, what type of evaluation improved face recognition, we conducted our first experiment. In this experiment, faces underwent either social evaluations or perceptual evaluations. Participants had to rate a set of faces based on social attributes, for example, how intelligent or trustworthy or dominant is the face, while rating other faces based on their perceptual attributes, for example, how symmetric is the face, how round is the face, and so on. We actually conducted this experiment twice, once with holistic physical features, for example, face symmetry, and once when we focused on specific facial features, for example, the hair, the eyes, the nose, and so on. Both experiments actually yielded the exact same results. During the test phase, we presented either old or new faces, presented from either learned views or different views. Now, let's take a look at the results. What we see here is actually that faces that underwent social evaluations were much better remembered than faces that underwent perceptual evaluations. These findings were very cool because now we know that social evaluations actually help us remember faces better. But we didn't have a control condition here, meaning it's also possible that perceptual evaluation, meaning forcing participants to focus on specific features, may have hindered face recognition. So we conducted this experiment again to examine whether what we see here is a social benefit or probably a perceptual cost. So we conducted this experiment again, now with a control condition of no evaluation, in which participants just passively viewed 1/3 of the faces instead of rating them, while rating other faces using social evaluations and other faces using perceptual evaluations. Once again, the test phase was identical. Let's take a look at the results. And what we see here, once again, is a social benefit rather than a perceptual cost. The social evaluations yielded much better recognition compared to both perceptual evaluations and no evaluations. And there was no difference at all between perceptual and no evaluations, either though the participants were much more engaged when they were asked to rate faces. So we ask ourselves, is it really a social effect, or is it possible that any personality traits will generate the same effect? So to examine exactly that question, we asked participants to rate a set of 80 different personality traits based on their social relevancy. So here you can see the ratings ranging from 1 to 7, and you can see that some traits were very socially relevant, and some traits were less socially relevant. We selected the top 5 and top bottom socially relevant traits. The lowest trait in social relevance were young, rich, strong, athletic, and tall, while the 5 most social relevant were sympathetic, nice, shy, charismatic, and sensitive. Then we conducted an experiment in which we asked participants to either encode faces using high social evaluations, low social evaluation, or perceptual evaluations based on the traits we just found. Let's take a look at the results. What we see here is no difference between encoding faces using high social meaning evaluation and low social meaning evaluation, with both of them yielding better recognition than perceptual evaluations. So actually both high and low social evaluation improved face recognition. However, I would like to point out that the traits in the low social evaluation were actually connected to high social status, because being rich, young, strong, athletic, and tall are actually all connected to being in a very good social status. And that led us to the next experiment. This study was done by PhD student Mayan Tredzwick under the supervision of Professor Galit Yovel and Professor Nira Lieberman. In this study, we examined the contribution of high and low social status on face recognition. We know that we all have higher motivation for social interactions with people from high than low social status. That makes sense. We then ask ourselves if we actually recognize better individuals or people that are linked with specific occupations that are higher social status than low social status. So to examine exactly these questions, we asked participants to learn a set of faces of women that were labeled as either doctors or cleaners, with doctors, of course, connected to higher social status and cleaner to lower social status. So the procedure went like this. During the learning phase, participants learned a set of faces. Half of them were associated with doctor labels and the other half with cleaner labels. And during the test, very similar to our previous experiment, there were old and new faces presented from new and learned views. So let's see if high social status actually contributes to our face recognition ability. So as we can see here, face recognition was better for faces that were encoded as doctors than cleaners, even though the only difference was just in the label associated with these faces. So we remember better faces that are associated with higher or better social status. So let's summarize the results so far. Associating faces with semantic information improves face recognition, as we just saw. We know also that trait inferences with either high or low social meaning improve face recognition relative to perceptual evaluations or no evaluations. We also remember faces better if they are associated with high than low social status. Overall, our findings indicate that person-related semantic information can affect face recognition, and actually language can affect face recognition. What's next? The study also intend to examine the development of this effect of semantic information on face recognition in younger kids. So hopefully once the COVID is over, the kids will be able to come to Dr. Chetrit's lab and participate in this study. I'd like to thank the MILA for their grant on this study that made it all possible, and thank you all for listening.
Thank you very much, Linoy. And last but not least, we're moving on to our second MILA's postdoc, Dr. Naomi Kahana. Please. Naomi, just unmute yourself.
Okay, you can hear.
Naomi,
Yes.
you're not in a presentation mode.
Exactly.
Now?
Still not. We don't see a presentation mode.
Okay.
Press the no. The lower part of the screen.
Now?
No.
Not yet.
Not a present. Really? Because
we see all the slides on the side.
Okay. Let's try it one more time. Now?
Now it's okay. It's okay.
It's okay? Great. Okay.
Yes.
Okay, so let's start. Thank you for letting me.
Now we see all the remarks on the side.
Oh my God.
Whatever you pressed, just unpress it.
Naomi, do you want me to share?
Now, do you see the...
No,
it's not in presentation mode, no.
Okay, now it will be very helpful, thank you.
Okay.
I'm sorry for the inconvenience.
So Naomi, stop sharing, please. Okay, here.
Okay.
Okay, we can see it on the screen.
Okay. Okay, so thank you for letting me present our work. I would also like to express my deep appreciation for your generous financial support. I hope this presentation will offer you a demonstration of both the theoretical value and the immediate clinical benefits of our research with patients who suffer from, unfortunately, from brain tumors. This wonderful project is the outcome of a collaboration between the MILA Center and the Neurosurgery Department at Ichilov Medical Center. I am honored to work under the supervision of Professor Naama Friedman. I am also grateful for the ability to conduct the research with two of the leading neurosurgeons in Israel and worldwide, Professor Zvi Ram and Professor Racheli Grossman. The aims of our research is to create a protocol in awake surgery, which I will explain about in a minute, to preserve language during the surgery and to identify language areas and tracts in the brain. Today, talk focuses on reading. We would like to share with you the first results of our study that aim to investigate the anatomical correlates of the reading process by examining the brain substrate of various dyslexia subtypes. In order to study dyslexia brain location, we chose a unique population of patients with GBM, which is a tumor that evolves rapidly inside the brain. In cases when the tumor is located close to functional brain areas, such as areas that are in charge of speech, or as in our study, written language, usually we are speaking about tumors in the left hemisphere. The rapid growth of the tumor damages the brain tissues around it, which causes a sudden functional deficit according to the tumor location. In our reading research, we included only patients who before suffering from GBM were intact readers. Some of them mastered 3 or even 4 languages, and then all of a sudden they became dyslexics. Awake surgery is an advanced solution that is suggested to the patients with brain tumor located in areas that are responsible for language functions. Surgery should be extremely cautious in order to avoid a permanent language loss. The surgeons want to be sure that they do not damage intact and necessary language areas adjacent to the tumor when they access the tumor and while they resect it. Therefore, as I will show you now, during this procedure, the patient stays awake and her or his language is monitored. Before the beginning of the resection and also during the resection and toward its end, when the surgeons want to determine the resection boundaries, a kind of simulation is conducted in order to predict potential damage. The surgeons applies a direct electrical stimulation to disturb the function of the brain tissues that they touch. If during this electrical stimulation, the patient shows a language deficit, the stimulated area is defined as a functional and should be preserved during the surgery in order to avoid additional language damage. In the following video clip, you can see how the neurosurgeon applies electrical stimulation on the surface of the brain while the patient is reading, and we inform the surgeon about the patient reading functions, which in this case are preserved. The tags, which you can see on the brain, indicate language zones that we identified in other tasks of syntax and word retrieval. Among the area that are in charge, I want to show you the video clip, sorry. Yeah. Naama, can you help me with that?
Sorry, it doesn't work for some reason.
Never mind, okay. Okay, so let's continue. Among the areas that are in charge of language, we can find fibers that transfer information from one location to another. Those are called association fibers. The inferior frontal occipital fasciculus, the IFOF, is a long fiber, serves that, to connect the frontal lobe, which is located at the anterior part of the brain and in charge of high cognitive skills, such as speech, to the occipital lobe, located at the posterior back part of the brain and in charge of visual perception. Interestingly, the IFOF is the only association tract that exists only in humans, which may imply its importance in higher cognitive skills, such as semantic processing, speech, and reading. This is a quote from Kohelet, who in his desperation wondered if there is any difference between mankind and animals. Well, he didn't know about the IFOF yet, back then. The IFOF transmits information between various endpoints. The one you see here on the slide are involved in reading. The Broca's area, which is responsible for language production, the occipital area, which is involved in advanced visual processing, and the superior parietal lobe, which is involved in space perception and integration of sensory input, and the posterior fusiform area at the temporal lobe, which is also called the visual word form area. So the patient who were included in this study had intact reading abilities prior to the tumor growth, had GBM tumors in language area, therefore underwent awake surgery. They all either demonstrated acquired dyslexia or and have their tumor located along the IFOF fiber. Of 75 patients who underwent awake surgery, we had 20 patients who met those three criteria. The reading process contains three main parts: the initial orthographic visual analyzer, the letter to sound conversion route, and the lexical route. Damage to each part causes different type of dyslexia. Although previous findings indicate that the IFOF is involved in reading, no studies so far has examined the effect of lesions in different loci along the IFOF on the different types of dyslexia. You will now I will now show you our results with regard to three types of dyslexia we tested and the location along the IFOF. Let's start with attentional dyslexia. Attentional dyslexia is defined by a selective impairment in ascribing letters to words when several words are presented together. It is manifested in substitutions of letters between adjacent words. For example, instead of reading goat call, patients with that kind of dyslexia will read goal coat. If the words are presented separately, they will read them just fine. In the reading model, attentional dyslexia is one of the disorders of the orthographic visual analyzer stage, which is the initial stage in reading, when we first recognize letters and letter order. Until now, the locus of this dyslexia was unknown. And then we tested where in the IFOF the attentional dyslexias are located, and that is what we found. We had 4 patients with attentional dyslexia, and the brain tumor of all of them was located on the upper portion of the IFOF, posterior termination, the back part that looked like a fan, just near its occipital cortex endpoint. It is important to clarify that none of our other patients showed this kind of attentional dyslexia. Interestingly, the cortical endpoint of the fibers that were damaged by the tumors of those patients is the visual association area that is involved in integration of visual complex input. I would like to show you now the reading of a woman who is a native speaker of French, German, and English, and she mastered Hebrew as well. At the preoperative comprehensive reading assessment, we tested her in all 4 languages. We observed a mild attentional dyslexia, which was evident mainly in Hebrew. During her awake surgery, when the surgeon applied an electrical stimulation near the IFOF in the area we discovered to be related to letter migration between words, she read isolated words without errors, but show a high portion of errors when reading word pairs. The surgeon did not continue to resect this area due to those functional boundaries in order to preserve her IFOF tract and reading functions. Let's try to hear that. Now, do you hear me? Can you hear that?
Not so much.
If you don't hear, I will leave it.
Maybe we can act. We can say what she was saying.
Okay. Okay. Okay, so this is a pair of word list that we gave her, and during electrical stimulation, that is that the yellow arrow indicate its precise location. She read, instead of saved waves, she read saved waved, and instead of dime 5, she read fine 5. Instead of bloom groom, blown groom. Even over, even oven. And when we stopped the stimulation, the electrical stimulation, she continued reading without any mistakes. So we believe that this example is a demonstration of the important theoretical application, and also we believe that this example is a demonstration of the important theoretical implication and also the clinical value of our research, which enable us to predict the exact functional loss and therefore fit a tailored reading test during the operation to save valuable functions. I will shortly describe our findings with regard to 2 other types of dyslexia. Phonological dyslexia is an interruption of the graphemic phonemic sublexical route, results in inability to read non-words or unfamiliar words, and also morphological errors, like going instead of goes, while the preserved lexical route enables those patients to read fluently familiar words. Deep dyslexia is a deficit in reading new words and non-words, just as in phonological dyslexia, and additionally in connecting the lexicon, resulting in semantic errors. Instead of reading happy, they can read a smile. Instead of read youngster, they read boy, for example. We identified 5 patients with a deficit in the letter sound route, 3 with phonological dyslexia and 2 with deep dyslexia. We tested where along the IFOF the tumor were located, and that is what we found. The tumor of those patients were all located near the IFOF and just anterior to the attentional dyslexia group, under the parietal lobe. We would like to suggest the disruption of the connection of the IFOF to the parietal lobe, that a disruption of the connection between the IFOF to the parietal lobe might cause the impairment in the letter to sound conversion. The 2 patients who had deep dyslexia had tumors that extended also to the temporal lobe. This leads us to hypothesize that the interlexical deficit, which leads to semantic error in deep dyslexia, is caused by a damage to the fibers that connect the IFOF to the temporal lobe, where the lexicons are. Surprisingly, we had 4 patients who, even though the tumor had attached to the IFOF, didn't show any reading difficulties, pre, intra, or post-op. Interestingly, again, they all share the same tumor location. The tumor were located under the frontal lobe, at the anterior part of the IFOF. Of course, those findings need to be further investigated. In summary, when we look at our patient's tumor location along the IFOF, we can conclude that attentional dyslexia is a result of injury to the IFOF connection to the occipital associative area. We also see that the phonological dyslexia may be caused by an injury to the IFOF connection to the parietal lobe. The information from the parietal lobe is later delivered by another tract, the SLF, to the frontal area. Indeed, previous findings localized the grapheme phoneme conversion route in the SLF. Finally, we would like to suggest that deep dyslexia is a unique, with its unique semantic errors in reading, is caused by a double deficit, a disruption of the connection of the IFOF to the parietal lobe and a disruption of the connection of the IFOF to the posterior fusiform area at the temporal lobe. It is correspond with previous findings that suggest that the orthographic lexicon is located in the fusiform area. Next year, we hope to meet you again and share with you our conclusion about the location of additional dyslexia. But that is for now. Thank you all for listening. And I'm sorry that I wasn't able to show you the video, which is, I'm sure you are happy to see, but never mind, maybe next year we'll overcome.
Despite some technological issues, I think you managed a great job at describing your very interesting research. So good for you.
Thank you very much.
Thank you, Naomi. And well, we can't believe it, but that's it for tonight. And it was very interesting to hear all of you guys. So thank you all. These were 8 fascinating lectures. I would like to thank all the speakers who shared their research with us, and of course, all their PIs, to the Cukier-Goldstein-Goren families for enabling all this research happening, to MILA's managing team, Yossi, Julia, Naama, thank you very much. And of course, to all of you guys for joining us today. Julia, Naama, would you like to say something? You can unmute.
I just wanted to thank all the participants and all the researchers in the background and everybody else who is associated with MILA, and of course, the donor families and the idea of establishing and funding such a wonderful center for innovative research. Hope to see you next year too.
Thank you, Julia. Naama.
Thank you, Orly.
Thank you very much. So guys, thank you very much for today. Please stay safe, healthy, and curious. Until next time.
Thank you, Orly. Bye.